invertible, right? A is invertible, meaning A has an inverse. If and only if 0 is or isn't an eigenvalue of A. Isn't. It has if lambda, if you have an eigenvalue of 0, that means that the determinant is 0 and the matrix is not invertible, right? Yeah, there's only the trivial solution to AX equals 0. Yeah. Okay, the determinant of A minus lambda I is called the what of A? Yes. Characteristic equation. Yes. Okay, last one. If there exists a P such that P inverse AP equals B, we say A is what? Similar to B. Nope. So before we start on today's lesson, I handed out a revised schedule for you. We're going to talk about the characteristic equation today. Why won't that? There we go. And then Monday, we're going to do diagonalization, and I'm going to give you a take-home quiz that will be due when you get back from Thanksgiving. Okay. And then Wednesday class will be canceled. Okay. Few what left? The big picture of linear algebra? It's coming. Yeah. All right, so let's look at the notes on the reading. So if you're looking for eigenvalues of a matrix, so last class, if I gave you an eigenvector, you could solve for the eigenvalue. If I gave you the eigenvalue, you could solve for an eigenvector. But we actually can find eigenvectors and eigenvalues without knowing the other one first. Okay, so in general, remember that the definition of eigenvalue, eigenvector, right, is that A minus lambda I times X equals 0. So you're looking for all scalars lambda so that that thing has non-trivial solutions X. Okay. But for that equation to have non-trivial solutions, the invertible matrix theorem says that the matrix A minus lambda I would have to not be invertible, right? Because if it has only the trivial solution, then A minus lambda I is invertible, right? So if it has non-trivial solutions, it has to not be invertible. No, something else. That was something to do with A, I think, not A minus lambda I. Yeah. Okay, so remember, also from the invertible matrix theorem, a matrix is not invertible if its determinant is 0. Okay. And so if I want to find eigenvalues, I want to find values of lambda that make the determinant of A minus lambda I 0. Because that would make A minus lambda I not invertible, which means that A minus lambda I times X equals 0 would have non-trivial solutions. Okay, so setting the determinant of A minus lambda I equal to 0 is called the characteristic equation of A. If you, without the equal 0 part, just determinant of A minus lambda I is called the characteristic polynomial of A. And the algebraic multiplicity of an eigenvalue lambda is just its multiplicity as a 0 of the characteristic polynomial. Okay, so if you get it as a 0 more than once, then it's just it's an eigenvalue more than once. Okay, so to use this, right, so this uses a lot of determinants because we're going to take in the determinant of A minus lambda I a lot. So we have to remember a lot of stuff about how to find determinants. So we had several methods that we learned. One of them was that you can put things in echelon form, not row reduced echelon form, just echelon form, and multiply the products of the pivots. But every time you did a row interchange, that changed the sign of your determinant. So that's the -1 to the r, -1 to the number of row interchanges. So one row interchange would become -2, -1 squared makes it positive again. So this is a theorem we learned and used in section 3.2. Also, you need to remember how to use a cofactor expansion to find a determinant. So we'll do a little bit of that later. And some properties of determinants that we already know that we're going to have to bring back and use today. A is invertible if and only if its determinant is non-zero. The determinant of a product is the product of the determinants. The determinant of A transpose and the determinant of A are the same value. If A is triangular, then the determinant of A is just the product of the entries on the main diagonal. And a row or column replacement operation on A does not change the determinant. So we'll do one. We've never done column replacements until today. We always do row operations. We're going to do a column operation later today. And the reason that you're allowed to is because it doesn't change the determinant. Okay. The resulting matrix will not be row equivalent to the original, but it'll have the same determinant. Okay. Determinant equivalent, yeah. Okay, so we want to add to the invertible matrix theorem and all other statements of the theorem. A is invertible is equivalent to saying 0 is not an eigenvalue of A. So if 0 is an eigenvalue, then you know your matrix is not invertible. And then we have the definition of two matrices being similar. We just went over that in the quiz. And similar matrices have the same characteristic polynomial and the same eigenvalues. All right, so that's about it for the really important facts. We'll do one example together, and then you'll work on your activities. Okay, so I've got a matrix A. It's just a 2 by 2, and I want to find the characteristic polynomial and then the eigenvalues of A. So the definition of the characteristic polynomial is just the determinant of A minus lambda I. So plug in A, right? So I have the determinant of, so A is just my 2 by 2 matrix, -1, this is too big. -1, 1, 4, 2, that's A, minus, what's lambda I? The identity matrix times lambda, which is, so instead of ones, you put lambdas. So this is going to be lambda 0, 0, lambda. So this equals the determinant of -1 minus lambda. So remember, when you subtract matrices, you just subtract corresponding pieces. 4 minus 0 is 4. 1 minus 0 is 1. And then my last spot, I have 2 minus lambda. All right, how do you find the determinant of a 2 by 2 matrix? AD minus BC. Okay, so this is just going to be -1 minus lambda times 2 minus lambda minus 4. A times D minus B times C. And then I can simplify that, and I get lambda squared minus lambda minus 2 minus 4, which is minus 6. So, right, so to find the eigenvalues, you take the characteristic polynomial and you set it equal to 0. You could use a quadratic formula, or you could factor it. Right, it factors to lambda minus 3 times lambda plus 2. Close. +3 and -2. So 2 eigenvalues. All right, so based on the eigenvalues, is the matrix A invertible? Yes, because we did not get 0 as an eigenvalue. Yeah. No, it can have 0 as well as other eigenvalues, yeah. And then it's not invertible, right? So that's just a little side note. It wasn't part of the question. So that's sort of everything that's new today. Creating a characteristic polynomial is just taking determinant of a minus lambda I. Finding eigenvalues is set that polynomial equal to 0. Now, finding the determinant of a minus lambda I can be more difficult if it's not a 2 by 2 matrix, right? So you're going to have to remind yourself how to find determinants of larger matrices. Yes?
So if we use the cofactor expansion on this, can we just use the result determinant?
Yeah, first you have to do a minus lambda I. Then follow the directions because I told you how to do it in the packet. Yeah.